Okay, so today we're going to go over section 7.1. It is an introduction to radicals. It is very, very basic. Actually, this lecture shouldn't take long. I think I've said that once before in another section. It wound up taking us an entire hour, but I really don't think today's going to take that long. It's we're not going to really look at any complex radicals, just basic simplification, showing you where they come from. Should not be that big of a deal. If you have questions, of course, ask me. But it is nice to have. It's nice to have this kind of short section to begin the week. But again, guys, we're in week 5. We're almost done. So I need you to understand that, or I need to go over review a little bit. If you're in the spring 2021 class with me, our final is going to be February, wait, if this is week 5, 6, 7. So Friday, February 26th, that's when the final is going to be open for you to take. It's not like the previous test where I open it and you have the whole, so many days to get it done. It is that day, and that's when you have to get it done. So I need you to understand to take time off. If you can't get time off from work, or if you know that that's not going to work, get with me as soon as possible so we can make accommodations. Don't mind making accommodations. I just need to know it before Friday, February 26th. Okay. So, I mean, we're almost there, guys. We've only got, 2 more regular tests? Is that what I'm looking at? Hold on. I had the schedule up a second ago. Yeah, we're in week 5. So we've got, we've got test 5 and test 6, and then the final. We're almost done. We're coming down the home stretch, which is awesome. Okay. So let's get to today's section. Again, this should not take long. We're going to go over just a very, very basic introduction to radicals. Your book, this is section 7.1. Your book covers it in a very nice way. I'm going to go over it a little different than your book does because I like teaching how to simplify these a little different. So if you already know how to simplify a radical, that's great. Do it your way. There's 2 main ways. I just really like the factor tree way, which is what I'm going to go over. And I introduce it in this section. So let's get into that. Let's get going. Do you guys, Avery, Kinley, do you guys have any questions? Or how about this? If you do have questions, just butt in and ask me. It's not a big deal. It might be hard for me to see the chat here in a second. Okay, here we go. No, I can see the chat. If you guys want to throw a question in there, not a big deal. Okay, so first off, what is a radical? Where does it come from? Well, your book really starts with explaining the square root and where it comes from, and where does it define it? It doesn't really define it anymore. Well, it defines the cube root. That's interesting. Well, yeah, let's just write it down. It says the number b is a square root of a if b squared equals a. So b is a square root of a if b squared equals a, right? So if we looked at something really basic like 5 squared, right? 5 squared equals 25. So therefore the square root of 25 is of course 5, right? That's what this is saying. So we've got b squared equals a. So b is the 5 and a is the 25. 5 is a square root of a, 5 is square root of 25 if b 5 squared equals 25, which is true. And we use this radical sign. So let's go over that in a second. So with the other way we can write this equation actually is that 5 equals the square root of 25. Now, let's kind of zoom in here to this radical notation. First off, it's really supposed to be written this way. Ooh, not an n, but a 2. Okay? Now that 2 is going to be your root. Sometimes it's also called an index. You'll see that every now and then. So that's your root or your index. For this one, it's the square root because when we squared it, we got the 25. Okay, so that's your root or your index. The number underneath the radical sign is called the radicand. Radicand. So you've got the root or the index over here, and you got the radicand underneath. And we're going to get to other, like adding and subtracting these radicals and multiplying. And the radicand turns out to be pretty important for some of those operations. So you'll hear me use that word radicand a lot. And just realize it's the number underneath the radical. And I typically use root but sometimes in the text you'll see index. So the roots here. So now look, if it's a square root, only if it's a square root, you don't have to write the 2, okay? So therefore, the square root of 25 can be written 2 different ways, okay? But when we get into cube roots and fourth roots and fifth roots, any other root other than 2, you have to write it. And there's nothing wrong in writing the 2 if you want to with the square root, okay? There's nothing wrong in that either. So there's kind of the basic, kind of definitions, I guess, of the root, the square root. So your book goes over then the principal square roots. It says the principal square root of a non-negative number a is its non-negative square root. The principal square root is written as that, blah, blah, blah. So what we're really talking about now is the common square roots. And this is where I'm going to introduce the factor tree, because some of us just don't know these off the top of your head, and you don't have to know them if you know the factor tree. So let's look at a really basic example where I'm hoping you know this already, okay? But I want to show you where it comes from. Let's say we wanted to look at the square root of 9. Okay, we wanted to find the square root of 9. First, I want to show you why it's 3, right? Hopefully you're all yelling 3 into your computers right now. But why is it 3? Well, one way to show why it's 3 is by doing the factor tree on 9. Now, the way you do a factor tree is you kind of write the number on the side, and you think of all the numbers that multiply into 9. Now, it is just 3 and 3, right? And because there's a pair of 3's here, and we're finding the square root, it means that the square root of 9 must be 3. So also, the way we can write this is the square root of 3 squared, right? 3 times 3 is 9. So 3 squared is just 9. And what happens is the exponent inside cancels with the root outside. And it leaves you with 3. Kind of neat. Okay, the exponent on the inside cancels with the exponent on the outside, and it leaves you with 3. So if we look at another example of this, let's look at one that's written more like a fraction, just for fun. So if we had the square root of 1/4, okay, the square root of 1/4. Well, what we have to do here actually is take the square root of the top and bottom. So the square root of 1 over the square root of 4. So if you see a fraction underneath a radical, you've got to take whatever that root is, you have to do it on the top and the bottom. So if we look at 1, what's nice about 1 is you can always, I'll do this up here. What's nice about 1 is you can always say it's just 1 times 1. So this would be the square root of 1 squared, right? It's going to cancel. 1's very manipulative like that. 4, though, we know is 2 times 2. So therefore, it's the square root of 2 squared. And these wind up canceling. The square root of 1 squared is just 1. The square root of 2 squared is just 2. So we wind up with 1/2. And it's kind of neat. Think about this. 1/2 times 1/2 is 1/4, right? Remember, when you multiply across. So we could have written this, and I'll write it. You don't have to write this, but we could have written this as the square root of 1/2 squared, right? Which leaves us with just 1/2. Okay, I know I'm overcomplicating this. So understand that if you're like, man, you don't have to do all this. I know that. I'm really trying to show you where this is coming from before we can just kind of do the easy shortcuts, okay? And we're going to do some easy shortcuts. Don't worry about it. But I do want to show you where it's coming from. And I'm going to utilize this factor tree, especially when we get to section 7.3, okay? Especially when we get to section 7.3. Okay, so let's look at another one. Let's look at, I'm going to steal one from your book. Oh, yeah. Let's focus on making these x squared. Let's look at it. What if we had a variable? What if we had like the square root of x to the 8th here? The square root of x to the 8th. I'll tell you, with variables, the way your book goes over this at first, with variables, the goal is to get this as something squared. Okay, I don't know why I wrote that radical so weird, but the goal is to get what's underneath here written as something squared. So what would I need to multiply 2 by? Remember, it's an exponent, right? I need to multiply something by 2 to get 4. Well, that's just, I'm sorry, 8. I gave it away. It's just 4, right? Like x to the 8th, you can write as x to the 4th squared. Now remember, there's a squared out here. You don't have to write it with the square root. But remember, there's a square out there. So because of that, these cancel and you wind up with x to the 4th. Okay? So the goal with variables is to think, well, how could I think of this variable term, the single term, as something squared? Well, it's just x to the 4th squared. So we looked at another one. Let's say we got the square root of x to the 22nd. Well, the square root of x to the 22nd. Okay, so we've got to think of what do we need to multiply 2 by to get a 22? Well, we got to multiply it by 11, right? And the reason we chose the 2 is because we have a square root, and these cancel, so it leaves us with x to the 11th power. Now, hopefully, you're going, but Mr. Shirley, all you're doing is dividing 2 into 8, and you're getting 4. 2 into 22, and you're getting 11. You're completely correct. That's the shortcut, okay? So this is the kind of the long way to think about it. The shortcut way is really with exponents, just with exponential terms. Doesn't work with the numbers, just exponential terms. All you have to look at is the root and the exponent and say how many times does the root go into the exponent? Oh, 11, okay? Now, let's say this didn't divide evenly. That's section 7.3. Okay, we'll get there when we get to section 7.3. So let's look at something a little more complex. Let's say we jump out of, actually, let's do 2 together, okay? Your book does 2 together. Let's say the square root of 49 y to the 12th. Okay, the square root of 49 y to the 12th. Now, what we're going to do here actually is I'm going to do the shortcut way. I'm going to think, okay, well, what's the square root of 49? These are being multiplied together. We can do this if they're being multiplied. What's the square root of 49? And then what's the square root of y to the 12th power? Okay. Well, 49, again, I'm going to do my factor tree, and hopefully you're just saying, but Mr. Shirley, we all know it's just 7. You're right. Okay. You'll see in 2 sections while I'm doing this factor tree. So we know since it pops out 2 7s, the square root of 49 is just 7. Okay. Now the y to the 12th. Well, okay, let's see here. 2 goes into 12 6 times. So we have 6, and there's no remainder. Guys, I'm going to tell you, got a preview. In a few sections, we're going to have a remainder here, and it's going to leave radicals. Okay? There's no radicals left over in this first section. It's all just nice, clean terms without a radical. Okay? Nice, clean terms without a radical. Okay, so let's go on. Let's go on to like the cube root here. So let's say I wanted to find the cube root of, let's do a number that has a cube root. 8 has a cube root, okay? The cube root of 8. And again, if I don't know the cube root of 8's 2 off the top of my head, I'm going to make a factor tree of 8, okay? So I'm going to make a factor tree. And I'm going to say, well, I know 8 is 4 times 2. And look, I'm going to stop when I get to a prime number, okay? 2. 4 is not prime, so I'm going to keep going. So I'm going to say 4 is 2 times 2. And I stop there. Now notice, up here I had 2 prime numbers of 7, and that meant the square root of this 49 was 7. Well, now we're doing a cube root, so I need 3 prime numbers. And I have 3 prime numbers, 2, 2, and 2. So because I have 3 prime numbers out of this factor tree of 8, therefore this leaves me with the cube root of 8 being just 2, okay? The cube root of 8 being just 2. Okay, so what about if we threw variables in there? Let's say we had the cube root of x to the 12th, y to the 3rd, something like that. Cube root of x to the 12th and y to the 3rd. Okay, so again, I'm going to do this kind of the shortcut way. I'm not going to make the parentheses, and this one would be cubed though if you were going to do this. I'm going to do the division in, okay? I'm going to say, well, how many times is 3? Now our radical's 3, right? Or our root is 3. So how many times does 3 go into 12? Oh, it goes in 4 times. Notice it's not under radical anymore because we can do that operation. Well, how many times does 3 go into 3? Oh, that's just 1. Now, you're more than welcome to write 1 if you want. I'm going to write it for now just to show you where it's coming from. And we're done, okay? This isn't so bad. Hopefully it's not too bad. I'm going to add a few more rules here coming up, but I just want to show you this stuff is not that bad. Okay. Let's kick it way up. Let's do like a fourth root. We'll do one like combined together. Hold on. Let's say we've got the fourth root of 81 x to the, let's do something that's divisible by 4. Again, if it like, let's say we chose like 22. 4 doesn't go into 22, right? Well, that's going to come up in section 7.3. Okay, so sit tight, hold on. We'll get to when that happens. Okay. So let's find this, the fourth root of 81. I want you to try this. Try this on your own. Take a second. We haven't done fourth roots yet, but it's solved the same way. Make that factor tree out. See if there's 4 of a kind. There is. Yeah, there is. And then do the x to the 20th. I'll give you just a second to work on this, okay? Okay, so let's start this. If you're not done, that's fine. Keep working. But I'm going to start with the fourth root of the 81. Guys, again, I know we probably won't see one that's different, but the reason we can take the root of each one of these is because it's being multiplied. Really what's going on, your book hasn't introduced this yet, but I'll give you a little hint here. What's happening is when you take a radical of two terms that are being multiplied, you can just take the root of both of those terms. Okay, I think that's coming up in the next section, or maybe 7.3. I'm not sure, but that's really why we can do this. But it doesn't matter. So the fourth root of 81, we put 81 here. I know 81 is 9 times 9, which is great. Look, that would be the square root of 81, right? Because they're both 9s and they match. But we're looking for the fourth root, and both of these 9s can go down to 3s. So check that out. We got 4 of a kind, right? 4 3s, nothing left over. There's not some random variable left or number left over. 4 3s. We're looking for a 4 of a kind. Boom, it matches. So the fourth root of 81 is just 3. And then x to the 20th. Well, how many times does 4 go into 20? 5 times. Pretty cool. Okay. You guys in the Zoom session, do you have any questions? Give me like a thumbs up just to let me know you're there. But if you have a question, ask me. Okay, please ask. Awesome. Okay. Let's see. Oh yeah, let's go over one of the rules now with these radicals that I kind of skipped over and I shouldn't have, but it's okay to go over at this point. And it has to do really with even radicals. We just can't take the even root of negative numbers. And I'm going to look how your book defines this for now so I don't get the wording wrong. Yeah. So the even root of a negative number is, now your book uses not a real number, not a real number. Okay, And eventually we're going to call this maybe imaginary or, not really complex. They're all complex. We're going to talk about this in section 7.7 a lot. Okay. So we're going to get there. But for now, if we see an even root and a negative number underneath, we're going to say this is not a real number. It's one of the two real glitches in algebra. And I'm gonna just talk about this for a second. Hold on, I'm gonna make you look at my face. Look, there's two, glitches is the best way to think of them. Two things that just don't make algebra correct. And one of them we talked in the last test. It had to do whenever we were solving out the rational equations, but then we had a restriction. Look, we don't know how to divide by zero. We haven't figured it out yet. We're going to talk about it in college algebra, actually. We're going to talk about what happens if we try to divide by zero, what happens if we kind of approximate what happens when we divide by zero, but we haven't figured out how to divide by zero yet. It just hasn't happened. If you figure it out, you'll probably get your name attached to it, and then kids learning algebra for the rest of their life will have to hear about your name or at least your method. Okay, the other thing we don't know really how to do or how to deal with are imaginary numbers. And by imaginary, I mean the non-real. When we take an even root of a negative number, which I'll show you here in a minute, it doesn't work. So we don't know how to deal with it. So what mathematicians did is they made a whole version of mathematics about it. And we're going to talk more about that in chapter 7. But there's this whole portion of math that really is dedicated to the imaginary number. And it was kind of intriguing. Like, yeah, when you start coming up with exponents and rules of exponents and then radicals, because a radical is just an exponent. We'll learn that in 7.2, actually. Radical is just an exponent. So it goes both ways. Well, then what happens if you have this negative? So let me kind of show you the math behind why it doesn't make sense. Okay, so let's go back to the document camera. Let's say we wanted to get an even root of a negative number that we know has a square root if it wasn't negative. Let's say the square root of negative 25. Right? The square root of negative 25. So 25, we know has a square root, right? But remember, the goal here is to get something underneath squared. And if we can get something squared, completely squared underneath, this cancels, and whatever is in here is your square root, right? I mean, whatever winds up being inside here. So a basic example, if it was just 25, let's see if I can, if it was 25, that would be just 5 squared and it would leave you with 5. Well, we have a glitch here if it's negative, because whenever you square any number, right, it turns out to be positive. It can't be negative. So there's not a number here that we can put in there that would give us back a negative, definitely negative 25, but any negative. So we have this issue. Let's see if I've got this. Look at this issue. Nothing's going to work. Okay? Nothing. That's a question mark. Nothing's going to work where if we have a negative under the radical and we have an even root. Okay? So even root, negative number. Okay? Even root of a negative number. So for now, for all the sections leading up to actually 7.7, we're going to say that this is just non-real. It's a non-real number. So that's like on this test, if this pops up, one of the options will be non-real number, and that's what you need to click on. Okay? Non-real number. So if we look at a basic example, if we had, let's say, the fourth root of negative 16. Look, we've got an even root and a negative number. So we're just going to say this is non-real. Okay, non-real. No big deal. So I'm going to kind of mix a few in here when we're simplifying that might wind up being non-real. Now look, if it's not an even root, we can simplify that. Okay, if it's not an even root, we can simplify. I'll show you. Hold on. I'm going to give you an example of an odd root. Let's say we had the cube root of negative 125. Okay, we can cube a number and get back a negative, right? I mean, if you multiply negative times a negative times a negative, you wind up with a negative, right? So you can cube a number and get a negative. That's why with odd roots, it's okay that they're negative. And let's look at that. I'm going to show you with the factor tree why this is true. So let's just look at the 125 first. 125 can be written as, I think it's 5 quarters, right? 25 times 5. There's our prime number. 25 can keep going. 5 times 5, right? So 125 can be written as 5 times 5 times 5. So it has a cube root, right? 5 times 5 times 5 winds up being 125. But also negative 125 can be a cube root because each one of these can be negative, right? Negative 5 times negative 5 times negative 5 gives me the negative 125. So I could write this cube root, because it's odd, I could write the cube root as negative 5 cubed. And it will cancel out, and it's okay that it's negative, okay? Because it's an odd root, okay? Odd root, not a big deal, okay? It's okay. And a lot of times when I see students simplify these, if they see an odd root, let's do another. Let's do like a fifth root. Let's say we've got negative 32x to the 10th, something like this. So if we've got the fifth root of negative 32x to the 10th, a lot of times students automatically, if it's an odd root, you could just take that negative out, okay? So what you can do is actually write it as negative, because it's going to wind up being negative in the end, because it's going to pop out at the end. 32x to the 10th. Okay, that's one of those shortcut things that a lot of students will do. That way they can just focus on the root, right? And not have to worry about the negative. Where if it was, let's say, we're going to get back to this one, but let's say if it was like the fourth root of negative 32x to the 10th, well, automatically we just say this is non-real, right? We don't have to worry about it because we've got an even root and a negative number. Okay, even root and negative number. So because it was odd, you can just pop it out. And if it's even and negative, just automatically go to non-real. We'll go into how to simplify these once we get to 7.7. You can simplify them, okay? It's just, we're just not there yet. We need to learn some more foundations of radicals before we get there. So now let's go back to this. Okay, let's go back to the negative fifth root of 32x to the 10th. And let's look at this 32 and break it down. I know 32, is it 6 times 6? No, it's not 6 times 6. 8 times 4, right? Yeah, 8 times 4. It has 4 is 32. Oh, neither one of those are prime, and they don't match. So let's just keep going. 4 is 2 times 2. Oh, there's 2 prime numbers. 8 we know is 4 times 2, right? And then 4 here is 2 times 2. Oh man, check that out. Whole bunch of 2's, right? 1, 2, 3, 4, 5. Perfect. Because we're taking a fifth root, not a coincidence, okay? So now remember, we've got the negative out here. We've got 1, 2, 3, 4, 5 2's, and we're taking the fifth root, so I can say that's negative 2. 5 goes into 10 5 times. Oh, no, gosh, not 5 times. I don't have that. 2 times. So 5 goes into 10. Imagine this is a 2. Actually, let's just rewrite it. There we go. There we go. Negative 2x squared. Okay? Negative 2x squared. Okay, guys, I'm going to pause right here. I'm going to see, do you guys have any questions you can put in the chat? If you're afraid to just jump in here. Or you can ask me over the Zoom call. Not a big deal. Okay. It's okay if you don't have questions. I'll just assume it's because of how great of an instructor I am, right? In my decades-long experience teaching radical terms and how to simplify them. Even though some of you are going, I know this other way, dude, it's so much easier. And it's because you were taught that way. Hopefully, it is easier. Okay, let's look at ones that are a little more complex, but then they still wind up giving us nice, even simplifying, okay? So I'm going to steal some from your book like this. Let's say number, this is number 48 on page 516. Number 48 on page 516. And it says the square root, remember there's no number written there, so we know it's a square root, 256 x to the 8. Okay, now if you get to this one, you're like, I have no idea if this is a square root. Now, of course, you can use your calculator, but I want you to know in the upcoming sections, numbers aren't going to have square roots, and you're going to have to break it down. So I don't want you to use your calculator by saying the square root of 256 for this one, for me, for this exercise, okay? I don't care on the test if you do that to show that I think it winds up being like 16 or something. I want you to show where it's coming from, though. I want to show you on this one where the 16 is coming from. So I'm going to first write out this 256. I'm going to go, you know what, 256, I know it's even, so I'm going to divide it by 2. So I'm going to take out my calculator, and I'm going to divide 256, second quit, 256 divided by 2. Oh, 128. And I'm going to circle that 2 because I know it's prime, okay? 128 is divisible by 2, right? Oh, my Lord, we're about to get a whole bunch of 2s. So it would be 64 times 2, okay? Now I can do the math in my head. 64 is divisible by 2. I'm choosing 2 because I just noticed these are even, right? 64 is 32 times 2. Man, we just did 32. It was like 5 2s. So if you want to just write 5 2s under here, that's fine, but I'm going to show you where it's coming from. 32 is 16 times 2. 16 is 8 times 2. 8 is 4 times 2. And lastly, 4 is 2 times 2. Holy cow. Look at all these 2s. 1, 2, 3, 4, 5, 6, 7, 8. There's 8 of these. Now, what matters, though, is we have a square root. Now, if it was an 8th root, this would just be 2, right? But we're doing a square root. So I want to show you how to do this kind of a long ways. Let me get another color up in here. Okay, yeah, we'll do red. We're going for square root. So what I'm going to do is I'm going to circle pairs of 2s. We've got a pair here. We've got a pair here. We've got a pair here. And we've got a pair here. So what that means on the outside of the radical, okay, we've got 4 pairs of 2s. So this winds up being 2 times 2 times 2 times 2. Okay, 1, 2, 3, 4. Because what we did is we actually took the square root of this 4, we got 2. The square root of this 4, and we got 2. And the square root of that 4, and we got 2. And the last 4, and we got 2. Okay, that's what's happening behind the scenes. But I want to show you where this is coming from. Now look, the square root of x to the 8th. Remember, it's an exponent. We just divide. How many times does 2 go into 8? 4. So this leaves us with 2 times 2 times 2 times 2. That's 16. X to the 4th. Okay, 16x to the 4th. Pretty nifty. Okay, you don't have to tell me. Let me see. I'm going to try to find another one like this to show you where it's coming from. Yeah, let's do, hold on. Let me, some of these I can make up in my head. Oh. No, that's not what I meant. Hold on. Okay, so let's say we did, this is, well, I'm making this one up. So let's say we've got the square root of 144 x squared. Let's add another variable here. Let's say y to the 16. I want you to try this one now. And again, don't use a calculator. I want you to do it this long way because we're gonna have to do this in a few sections. Okay. So I want you to do this one by hand. You're kind of cheating yourself if you just pop in the calculator. Okay. I want you to do this one by hand just because we're going to do this a lot. We're going to have to do it the long way in the next few sections. I'll give you a minute to do that. Okay, so let's work. It's okay if you haven't finished it, but let's look at 144. So I'm going to do the same thing over here with 144 that I did with 256. 144, it's even, so I'm just going to pop it in my calculator and say 144 divided by 2. So it's 72 times 2, right? Now 72, I know that 72 divided by 2 is 36. 36, well, it's 6 times 6, right? You could stop there, actually. I'm going to keep going. That's 3 times 2 and 3 times 2. So I went all the way down. This is a lot going on. 1, 2, 3, 4, 5, 6. 6 different prime numbers. And then we actually have 2 different types of numbers. We've got 2's going on and we have 3's going on. So this is actually why I chose this question, okay? We've got 2's going on and we've got 3's going on. Okay, here we go. So I'm going to, look, it's a square root, right? So I'm going to group these together with pairs again. So I got a pair of 2's. I got a pair of 3's. And I've got a pair of 2's here, okay? It would have been easier if I wrote them together, but I want to show you where they're all coming from. So therefore, the square root of 144, look, we're taking the square root of each one of these bubbles. So the square root of 4 gives me 2. Since we had a pair of 2's, pops out of 2. We have another pair of 2's here, so it's going to pop out another 2. And a pair of 3's here, so it's going to pop out a 3. And then we get the square root of y to the 16th. That's just y to the 8th, right? Now, 2 times 2 times 3, that is 12. Y to the 8th, okay? Boom, we have taken the square root of this number. Okay. That'll be probably one of the hardest ones you do. Yeah. So I'm going to stop there. If you guys have questions, ask me. I'm going to write out the homework. But the homework is for section 7.1. Let's start on number 7. This is on page, it starts on page 515, number 7. Do 7 through 17. It's all going to be odd. Skip over that one part. And then 25 through 47, and then 61 through 81. Now, all these are odd. This actually isn't as much as it looks. These are all odd. You've got to get this done before you go on to the next section, before we go to, or not really 7.2, but before we get to 7.3, okay? You've got to get this done. It'll make it so much easier when we get to 7.3. Okay, and I'm going to suggest that you don't use your calculator unless you just need to do basic little division stuff. Don't use that square root button because we're not going to be able to use it really in 7.3. Because we're going to have numbers that aren't square rootable, but we're still going to use this factor tree to solve it. Okay, you're going to thank me when you get there if you didn't use the square root button.